Sì. Vai. Scusate, intanto che arriva, possiamo cominciare a prendere posto? Partiti lui. Per piacere, potete riprendere posto così abbiamo... e soprattutto manteniamo il tempo per la discussione di dopo. Hai 20 minuti, ti do i 5. Hai 15 minuti, ti avviso che mancano 5. Ok. Okay, we can start now, please, with the first speaker of the second part of this morning. Silent, please, can you close the door? The first speaker, this is second part, is Marco Molinaro about astrophysical resource interoperability. You have 20 minutes plus questions. Good work.
Okay. So thanks to the organizers for inviting me over to this workshop, and thank you everybody for attending. I'll try not to be too boring for you. This will be quite basic presentation, quite basic talk on what astrophysical resource interoperability is. I recently, or not so recently, got the impression that some of the, let's say, key things, key topics and information on this is not completely well understood, so I will be really, really basic. Don't take offense on this if you already know these things, but I will go quite slowly on this. I will be speaking, but of course I had a chance to coordinate this thing with Fabio and Giuliano also. So I won't tell you what astrophysics is. But you'll see that I explain the other two terms in quite a while. This is the basic outline of the thing, so interoperability and how does that cope with open and fair. A quick look into the integration in the EOSC scenario and the VO take-up in the community. plus some conclusions or summary if you want. So what is a resource, just to start? So the IVOA, the bottom part, for the resource metadata for the virtual observatory directly refers to the top part, that is the World Wide Web Consortium resource definition. And the resource is whatever might be identified by a URI, so a Uniform Resource Identifier. So whatever thing you can attach an identifier to is a resource. In a sense, I am a resource, okay? It's strange, but you can do that. A concept, a theoretical concept, is a resource. You can attach an identifier to that. So resources, while I will be speaking, means every single thing you can describe. And that's why the last sentence there says, we expand on this definition, but by saying that it is also describable. That's the metadata you attach to it. Okay. And getting back to Riccardo's talk, DOI has metadata attached. So whatever you describe with a DOI is a resource, and so on. You can go on. And then what's interoperability? Okay, this is also something that you may just think, okay, I know what's interoperability, but I wonder whether you never experienced opening up your word processor, typing interoperability in, and you see the red underline under it. That means that usually it's not a common word. There are many definitions for it. I like this one that simply says it's a characteristic of a product or system to work with other products or systems without any restriction. And that without any restrictions automatically requires you that if those systems have to interoperate, they have to rely on open standards. And here's the first reference to open and openness. That is another largely used concept, but maybe not completely understood. And also interoperability, since it's quite not debated, but it can have many flavors, many levels. I will be referring to mainly two levels. One is the syntactic interoperability, and there you speak only on, let's say, data formats and structured content that you distribute or share around. And this one is quite simple, but in itself is a prerequisite to the other level that I put in there, the semantical one, where you don't only share the content in a structured way, but you share the meaning of your data. That's why it's semantic. And to stress the open standards to have properly interoperability, I also put that drawing there, so you can see the difference between compatibility, de facto standards, and interoperability. You have a PDF, that's a PDF displayed on the screen. PDF is a standard. It's a de facto standard. It's not open, so you can share it, but you can hardly say it's interoperable. If you want to change something there, you are not free to do so. You have to go to ADOP and change the content of the metadata. So these are the two basic things that we move on. And speaking about syntactic interoperability, astrophysics has quite a long history on it, because it's 4 decades that FITS is around. That's a format. It's well defined, it has changed in time. These are just 3 excerpts from the introduction of the 4.0 standard document for FITS. And this is really what gives you the syntactic interoperability in astrophysics. And this is also what allowed and allows also nowadays the preservation of the astrophysical data. You can read FITS that are 40 years old just because FITS is backwards compatible and gives you that syntactic interoperability. But of course, astrophysics moved on. Here I simply stole a slide from Catania ECT meeting from Fabio. So from fits, you moved on to other formats, to other ways of dealing with data, to other ways of processing data, to other way of building software also for big projects. And on the right side of this image, of this slide, you see appearing the VO, the Virtual Observatory. So that's where we move from syntactic into semantic interoperability through an organization, the IVOA Alliance, that is an open standards organization. That means that develops those open standards that are needed for interoperability in the astrophysics domains. And it's not only open standards, also the governance of the IVOA is open. If you have something you don't like in, well, just okay. It requires you some effort, but pick up your mail and send an email to the IVOA people. They'll probably, well, they may shout at you, but they will also give you some answer usually. And how this is related to the openness and then also to the fairness that nowadays we are speaking of. IVOA as an architecture, this is the level 0 architecture, so you have the resource layer at the bottom, the user layer on top, and you have the two columns for finding and getting your data, and the VO core inside that lets you have the interoperation. Speaking more IVOA or VO jargon, the finding thing is called the registry, is where you put your resources. You know the identified things, the resources before, so you put an identifier in the description and you have the resources there. User browse through it and get back information that includes semantics, modeling, formats, and access points that rely on standard open protocols, and that's the other part. And how this is related to openness. So what's open? Open science. Open science is what involves transitioning from a system in which it is difficult to access and locate the results to that one that openly distributes the results. So if you have resources on one side, that means data storage, preservation, computing facilities, you can put services on top of it, building interfaces, creating catalogs, not object catalogs like in astrophysics. This is catalog of resources or catalogs or whatever you want, and tooling on top of that. This is not open because you are designing it. This is custom. This is what you want to do. But if you want to go a step further, so to remove the difficulty, you have to put your metadata, your persistent identifier there, and rely on semantics and models. When you do so, and those four things are exactly the core that I showed you before, you get open data on one side. You get open access on the other side. The intersection is what makes it interoperable. So you remove the difficulty, and you have your open science there. That's how also IVOA works, and that's why I state that Virtual Observatory makes astrophysical resource open. And then for the FAIR principles, this is just the box from the Wilkinson article published in Nature in 2016, even if the FAIR principles are, let's say, older than this. I won't go through it. It will require a talk on its own, going through the description of these kind of things. But you see there's written metadata everywhere. You have globally unique and persistent identifiers. You have to explicitly include the identifier. You have the identifier using a standardized communication protocol. Protocol is open, free, and universally implementable. So there are all of those things that really require openness. And interoperability, you have to be sure that your meta and data use formal, accessible, shared, and broadly applicable language for knowledge representation. And the vocabularies that you use have to follow the full stack of the FAIR principles. So interoperability is not easy in a sense, but if you reach to that point, your data can be understood by the others. That's why we are speaking semantics, interoperability. And how is IVOA attached to this? Well, it's quite simple. If you are findable, you have the registry there for you. If you want accessible, you have the data access protocols there. Interoperability is the core of the VO system, and reusability engulfs them all in a sense, because it's not simply on the resource layer when you put metadata curation that makes your things reusable, but you have to have the full environment for it. So this is the attachment of the, let's say, astrophysical interoperability in terms of the VO scenario, written down in terms of the two current buzzwords for these kind of things, that is openness and fairness. How was that all of this how was evolved and how was developed at the European level? Here is a, oh, there's a missing parenthesis there. Okay. There's, let's say, a timeline of the various projects that dealt with interoperations at European level. You have various levels, so you have Astronet, you have the Opticon project, and you have the EuroVO continuing on up to Asterix. And these ones are now facing what's the EOSC that Fabio was just speaking before. That is a solution for open science in a cross-domain content. At the H2020 context, at the, let's say, EOSC level, there exist cluster projects that are starting to cope with its open science cloud. One of these clusters is ESCAPE, and is the first step, in a sense, in cross-domain interoperation in physics domain, because you have astronomy and particle physics really tied together, while before it was astroparticle physics, more or less, not exactly physics in a sense. And one of the challenges there now for the VO is the integration. This is dealt with within a work package, and the, let's say, the challenge from my point of view at least is that while continuing to update, upgrade, and develop the VO framework for interoperability, there's the requirement to integrate the architecture of the virtual observatory that is already existing and operational into another full architecture that is forming. So you have to be sure that they don't destroy or go orthogonal with respect to what you are doing, and in the meantime, you have to find a way to reach a larger audience than the simple astrophysical thing. So, but apart from this digression on the European level and the EOSC thing, what are the outcomes of the IVOA or the VO framework? In the end, you have a lot of standards. Don't worry if you don't read it. It's not important, of course, to read the single blocks there. And it's slightly less, slightly more important how many standards and how does the continuously evolving VO scenario is there. But what I would like to go through is not the standards, but how they are taken up at various levels. In various parts of the world or in various areas. Well, we have seen yesterday presentation by Severin. So that's where VO has been really taken up, or more than taken up, was starting from the VO to develop the full architecture of CADC. And you'll see in a while a smaller, let's say, experience by a scientist directly that tried to simplify her life in creating a merged catalog of really, in this case is a catalog of astrophysical resources, of astrophysical objects, and see whether this worked or not. You'll see this one. And I'm going a bit back and forth because another example was explained yesterday quite clearly by Magda Arnaboldi on the ESO science portal and the programmatic access that is behind it. So VO technologies and interoperability are not these strange things. Big stakeholders are using them. I won't go through all other examples. I just report you here the ESA Sky as an image, but you have the CDS and the Vizier and Simbad tools that and well, it's not exactly tools, it's databases with interfaces and way of searching through it. You all probably use them. I won't tell you what they do, but they have VO attachments quite tight to that. And you have tools that use VO technologies, and AstroPy community is getting, again, near the VO, and PyVO is revived, and so on. What about the Italian level? So here is just a small picture based on my expert experience inside the Italian Astronomical Archives data center, trying to push the data resources there through VO services. All of these are some sort of timelines on how I had to change a bit things to go through. So we have some experience there. And the bottom part, I'll ask you to wait for Fabio Vitello's presentation layer on the VO LKB that is not exactly VO, but is becoming VO compliant in a sense. It will be, all those resources will be available through VO interfaces and not only through the custom ones that are available there. And this is probably the last thing that I will tell you is that in time we had some resources deployed in the IVOA registry from our data center. You see they are ramping up initially, and then now they are reach sort of a plateau. I won't investigate this. I'll just tell you that it's not because we don't have any other resources to put in there in terms of data collections or things like that. There are other kinds of resources that are missing to make that line go up again, okay? And so some summary, conclusion. Despite, maybe I shouldn't say that, despite what was saying, I think, our scientific director at the start of the morning, interoperability has a long history in astrophysics. So it's not that we are facing new things, at least in that sense. And I wouldn't say that we have to learn from other communities also in the management of large data. Depends on what you want to preserve and what you want to describe. Interoperability, anyway, can be said it's hidden or invisible. That's fine, as far as you know that it's there and it requires resources to stay there like that. And interoperability is multifaceted. I just explained you a couple of levels where interoperability can be taken into account. But of course, it's not simply letting byte blobs move around the net. That's not interoperability. And the VO is a full framework of interoperations. It's not a software layer. And you can see that through the FAIR principles if you go through the details, into the details. And the VO technologies and the standards required a lot of effort from many, many people. Please don't waste that thing. I don't want people just saying that, okay, VO is there, we use it or we don't use it, doesn't matter. There's people that have put efforts in there. And also VO may be considered an old acronym, maybe a worn out concept, but it's an evergreen open approach, actually. It just changes the name, but it doesn't mean it's wrong. Of course, it's not static. New requirements are coming in. So you have now computational resources to be moved side by side with the data resources. What does it mean to be interoperable there? This is something to work upon. I don't think it's completely clear, but that's it. And also on user authentication and authorization, there's a lot of discussion, but please don't make the wrong assumption that you can put authentication over everything, because that complicates the life of those that don't need it, okay? And also machine learning techniques may have different requirements that human users in accessing the data. And that's it. Thank you for your attention.
Thank you, Marco. Any question?
Marco, I have a question about the open concept and the interoperability. Let's put it in this way. So in order to have open sources, we have inside embedded interoperability. So the question is, we know that interoperability is a necessary condition in order to have open sources and open data. Is it sufficient condition?
You mean is interoperability
Is it necessary and
enough
sufficient?
to,
Yes.
okay. Openness is a general thing. No, you need preservation also to have it. You don't need only interoperability, in my view. I mean, interoperability can give you the full framework, probably from the data resources up to the computational ones, because you can speak interoperability also there. But then you have to maintain this thing over time. So you have to have curation and preservation of what you have there to be completely open. So it's maintenance also. Yes.
Okay, this goes very well in line with the idea of preservation of data, what actually Riccardo taught. And
for example, yes.
okay, thank you.
Any
a comment. I would like to point out that although for most of the science communities, FAIR principles are enough to have open science, I think that astronomy is more demanding, in the sense that, for example, one of the FAIR principles says that when data are not there anymore, I can't remember which one is it. It's one of the two ones. It's well, whatever.
A2 metadata.
A2 exactly. The point is that for us, we need to preserve the data, the pixels actually, forever. Because in a sense, what we observe, anything we don't observe at a certain given moment of time is missing data. We don't want to miss data that we already have, which is, so it's an additional requirement.
Yeah, sure.
Plus the ones of allowing some service running, doing computations on the data to simplify the access, which I mentioned in my own talk. So FAIR is not enough for us.
Yeah, I agree on the comment, only I don't consider myself an expert on computation, so I didn't touch that point. I just put it as an extra thing. And it's true that FAIR is a set of principles. It's the way you say now you have to be fair, there has to be fairness in the data. My statement was that through IVOA we already have reached that point. It doesn't mean that we can go farther.
Probably this is something we can discuss during the discussion, but we'll just introduce this part. I mean, I have been supporting VO since the beginning. Riccardo knows about it. I've been at the first workshop, I've been at the first others speaking about this. And at that time, I raised some issues. And I wrote these issues, nobody replied. But first of all, it's still, because I don't know anymore about the political within the VO, is still a project like, is it run like a project? It means that only people that really do or are involved directly can take a decision, can in some way drive the stuff. Because at that time I was involved, I was still a radio astronomer at that time, I was involved in a high energy TV project, and the TV community and the radio community was completely missing in the VO project. And I raised this issue. I repeat, nobody replied. And the same for other issues, technical, the pixelization, so forth, that sometimes came in, you know, the HIPs, the MOC, the LPX, whatever. At that time I raised this issue. Again, no replied, but after 10 years, somebody realized that you need this. So anyway, this was, I think, just an introduction for the discussion about the VO that I still support.
I won't defend 100% the way the governance IVOA is done or how the technical coordination group works, even if I'm within it. It's true that you have to provide some effort and to make you visible through things. It's not just dropping an email for a feature that you can see that feature show up. Okay, that's true. Because, for example, if you want to touch a standard and then modify it, what the standard process requires you is to have 2 interoperable implementations. So if it's only you asking for something, you have to find someone else with your same requirement that side by side with you demonstrate that it's useful, fulfills a use case, and is interoperable. Okay. I know it's an effort. That's where the national projects should help. That's why I was putting this building a community in the hand. Because I know it was quite of a restricted party, maybe in Italy, in the last years. So it's not, I feel a bit alone sometimes in this party, okay? So please just come and shout at me, it's fine.
Okay, thank you very much again. Okay.
Okay, hello everybody. So I'm going to talk about well, virtual observatory for some services. You have here a list of a lot of names actually. There are people in here in the audience that during the last years we have worked on different projects with them. Before I start my talk, I'll start with the title actually, Enough Science Archives and Big Data Challenges. And I want to point out one thing about big data. So what differs big data from the real data? Because, well, we are in the age of, you know, in this epoch of big data stuff, but what is the main issue, even if you Google it, you'll see that the difference between the big data and the data actually consists of 3V. They call it 3V. So in order to have a big data, we need volume, we need velocity, and we need variability. What I'm going to talk now are for some scientific cases that we want to connect with the infrastructure and with the computational resources in order to make these resources open. So it's a talk about interoperability. So very nice introduction from Marco to say when I talk about the IVOA here, in the next minutes you understand why these particular cases could be attached to the data and to ICT sector. So yeah, there are 3 cases. If you see here, it's an exoplanet case. So we have image instability simulation. We have one integration function of Matisse. There are 3 things. All of these things, they're connected with the planetology. So I'll talk about the planetology and for the services that we developed in planetology in INAF. So this is, let's say, tradition that we made with ASI, with IAPS, and now in Trieste. And these 3 services actually will explain more clearly how we can take some scientific problem, how we can use the resources to make simulations, because all about here is about simulation modeling, and how we can integrate this data in the big data resources in catalogs, and how these catalogs can be accessible to the community. This is the first thing. The second thing is how we can use these resources for what we call it real-time computation. So it's connected with what Fabio talked before and for all these huge projects that now people also in planetology and Europlanet concept, in the Europlanet Society, which is part of the scientific efforts in Europe, is how to distribute the sources. So we have resources in different countries, and in different countries we have data storage, we have data processing, and of course distributed sources, but we have something centralized that use them to interact between them and to use the best resources from each side. And what I'll talk is, okay, big data. So I'll not talk about big data because all what you see here is small data actually. But I'll talk about the variability of the data, and I talk about the velocity of the data, because we'll be capable, and this is especially the last tool that Angelo Zinzi will talk later in his talk about, Matisse, that we can get some data on fly, so we can send your request, we can run some simulations on your request, and while you're waiting in your office, you can get the data. So I have 12 minutes, so I talk about 3 already. I'll be a little bit faster on this, but I'll start with VESPA. So this is Virtual European Solar and Planetary Access within H2020 Europlanet project. INAF was involved in this project. The website is VESPA, and you see it here. What is the interesting part of this? INAF participated with services, and what you see is actually a window with a database. So this is the VIO table. This is the interface of the service that we developed, and this is particularly for the NASA dust catalog of particles that they were captured. So what is the main part? I wanted now to show in the next 2 slides some really technical stuff. But the message is that it's all about the metadata and for the data connected with this metadata. So it's very much connected with the interoperability that Marco talked before. So, well, maybe it's very difficult to read it, but my point here is not to read all the things. The main part is that you can see in some description. So this is the file that you need. This is the descriptor file thing. This is a descriptor file that actually, the idea of these 2 slides is to show that it's very simple actually. If you enter and you develop such kind, if you have a template of file, you can use such kind of template file, and you can very easily, if you have a small database, you can very easily make this database available in a so-called virtual observatory. The only important thing is to make compliant. And compliant, you have a particular parameters. You have a virtual observatory standards and IVOA standards. So you can use this part in order to make your services available to the others. All the idea of this descriptor is actually to make all your database common for everyone. So everyone has different now. In all the community here, we have different data sets from different scientific fields. If we can describe all these data sets in a particular parameters that are known for everybody, once you know these parameters, you can get the research on this database, and you can learn from the other part. And we are now in the era of the multi-messenger astrophysics, so this is extremely important for this. So here we have actually the metadata, and after that you have additional column that you saw before that you can define just with a simple script in the XML file that you see here. And when you go to this is actually 4 snapshots of this file. It's very simple for exactly this data service that you see. So after that you can just ingest the table. You can put the data with different parameters that I described here with this particular protocol, EP and TAP protocol, that are these parameters are embedded. This description of these parameters are described in this protocol, and after you just execute this table, and once you have this file, so you saw it's not very very big, you get actually this service here. So in the next few slides, I will talk about the different scientific cases. Giuseppe Morante earlier this week showed the database of the exoplanets. So the efforts in the European community in the next call, which was actually this year, it was about planetology, but you know that now hot topics in planetology are exoplanets, and we have, in Trieste, we have this Artex archive. It's not only Trieste, we have a GAPS also, and what I want to point out here is actually 3 services that are connected with data and results from simulations. So this is the first service, on the first surface. This is the first study scientific case. And well, you have here the link. What I want to say is actually we have description of the parameters. So this is archives that actually simulates terrestrial type climate planets. And because we don't have observations, the idea of this model actually is to give complementary information, which is one of the main things of the modeling, because it's not only to calibrate the model with the data, but the model works not only to get prediction, but the models usually work to get you complementary information that the observation cannot give you. And this is the idea of these cases. So you have parameter names, you have results, and when you go to the data, which is to the let's say to the database that are maintained by IVOA, okay, IVOA 2. So we have here exoclimate archive. We can choose the parameters. We have stellar parameters, planet geophysical parameters, and when you make a search, we can end up with such kind of data. So where just images, if you go and you click on the images, you can get on the file, you can get such kind of simulation results. This fits data. So we want to put only 3 minutes, okay. So 1 minute for each service, okay. So, but after that, maybe I can go for a discussion. So we can create such kind of data service that we want to do. The next case is MAG simulation. So I developed a model that studied the chemical instability, what you see here, typical chemical instability and tearing multi-stability, and I applied this model to Mercury and to the Earth. So in case of the Earth, we can see how actually magnetosphere interact with the solar wind, and we can get some idea how we can transfer momentum in these particular cases. So this is the typical results of such kind of instability. So these are the data that will be available in such kind of data services. You have magnetic field here, typical for the tearing multi-stability. You have different velocity you can compare, and this will be also accessible like a data. And this, for example, is already scientific case that can be used for the next Bepi-Colombo mission, for the Bepi-Colombo mission based on the messenger data. And what is the interesting part is you have very simple organization of the data. It's very small data, and you can structure very well such kind of images in order to study such kind of stability. The second part is Matisse. Now, because I'm running out of time, but Angelo will talk more about this. We develop a real-time, actually, almost real-time computation of the aerodynamic coefficients. What does it mean? When you have a body in rarefied gas dynamics, you need, in order to calculate the gas drag, you need to calculate the aerodynamic coefficients. For sphere, it's very easy. There is an analytical formula, but for the irregular shape, it's not easy. And actually, it was one of the main crucial things for dust dynamics in Rosetta mission. So we developed this. As you know, Italy participates with 2 instruments in Rosetta mission. So we developed a code that calculates such kind of parameters. And with Matisse, what Angelo actually incorporated in Matisse, and you show here the interface of Matisse, is that when you can go to Matisse and you can choose the parameters, whether the shape, for example, we took ellipse to it, we can put different aspect ratio of the irregular shape, and you can get these coefficients. Why these coefficients are important? It's not only for the particular case in comets in rarefied dynamics. It calculates aerodynamic coefficients for any kind of body when we talk about the rarefied gas dynamics. So it's a common thing that people that can go, they can take this coefficient, they can use it in their codes, because most of the state-of-the-art code, they use spherical grains. And well, these are the data, and I want to go to the last slide. Actually, what about INAF, and what about planetary services, and how IVOA actually supports this, and why this is important in order, because this is a community to talk about archiving and for the big data challenge. So we propose, actually, Italy participates in the next call for the Europlanet 2024. Trieste and IVOA, we proposed services, to develop services, but what is the main part is that Italy will become the regional hub of such kind of services. It will be one of the 13 of Europe if this proposal passes. So actually, IA2 and INAF will have a crucial role about services in Europe. The other one is in Paris and the other one is in Germany. So we propose also machine learning case, which is together with IEPS. And last but not least, we have geological mapping of planetary services. All this is about for a new call, which will cost 10 millions if we are lucky and we get this funding in Europlanet. From the European community, we can be able to develop such kind of data services part of INAF. The idea is that we can get resources for this and hopefully we can foster a little bit this ICT and data scientist issue that, you know, Italy, it's crucial, like it's an important place to develop such kind of scientists because we have actually a very strong background on this. Thank you very much.
Okay.
Yes, please. Ricardo, over there.
When it comes to preservation and curation of these data, this is a tricky question. What is your expectation?
Well, for example, for the previous, well, actually, it's the code that is going on, actually, the project that is going to end in September. It was 2020. We have these data services, you can see in this Vespa, and they have, in the contract is written, they have to maintain these services. But the idea is that data services, yes, the data services. Storage, yes. The idea is that European community gave in the last course, actually, Marco showed that the idea was to develop the infrastructure. Now the European community says, we developed already the infrastructure, we will not give you any more money for the infrastructure. We want to give you money to develop and to maintain this infrastructure. And one of the main things when we were preparing this call was that they said, for example, we don't want, and this was a very strong message, to organize workshops on scientific fields, which was very strange because anyway, this is scientific data. But they said this is very important to maintain the data services because everything what we'll talk about in the next years is to maintain the data, the services and the infrastructure that we created. And this is very much connected with transnational access, with these distributed hubs, the supercomputer that last week European community released that there will be 10 members of the European community and Italy is one of them that will develop this supercomputer to sharing this data and resources, computational resources. This data will be preserved. All these data services will be preserved and this is included in the proposal. It's a pity that actually there are a lot, actually it's good because, for example, in the new code, there's so many people, so many institutions that are involved that the funding is very low because still the total amount is 10 million, but if there are more contributors, you get less money. So to preserve your data, you need, you know, storage, you need resources in order to keep this. Fortunately for this, you can keep it still with the money that they were already, let's say, assigned in the current project.
I remember that IA2 is the infrastructure proposed to maintain data from long preservation, and there is also, of course, a laboratory for developing a new one. But the main infrastructure, IA2, the evolution that we have to Technopole and so on.
I want to be more specific. I mean, my question was, you maintain the service as opposed to maintain the data. I mean, now, I think you implied that the computational complexity is similar to the cosmological simulations. Is that right or wrong? It is similar.
Cosmological, it's much harder, I think.
Well, they can go harder too, but
yes,
so they're
because
similar.
it's huge data there.
So what I'm saying is that and that is the reason why you preserve this data, because otherwise simulations, that special case of observations, quote unquote, errorless, that in principle you can replicate exactly. So in principle you only need to have the metadata, but you can replicate the simulation anytime you want if you have the service. You see the difference? It is the only case, because otherwise when we observe the sky, if we don't make the observation, we lost the opportunity. That's not repeatable anymore. Okay, but simulations, it's something that we can repeat. Okay, so
Yes,
this
the question
okay.
is that
That's
you
what I
have
mean.
always trade-off of the computational power, the resources that you put. So if you have a library of simulations, you don't need to run these simulations again. So actually, of course, if you miss your chance to see if your observation, of course, it's very, it's unique thing. For simulations, yes. In this case, it's much more, let's say, calm because you can restart everything. But the resources that you use to make this library, it's also sufficient. Yes, and yes. Yes, okay.
Okay, thank you very much. Sorry, it's changing, but I try to gain sometimes.
Nice. Okay. Okay, perfetto. Hi everyone. Let's see. Okay. I'm Eleonora Lei. I'm a PhD student at the University of Padua with a fellowship at the INAF Observatory of Padua. And in my PhD project, I work with exoplanets, in particular with exoplanetary atmospheres. But I also handle data, as we will see. In particular, in this talk, I will deal with a code that I developed concerning a merged exoplanet catalog that collects all of the available data coming from the actual online catalogs and sorts them in a peculiar way that in the end we will end up having a standardized version of the exoplanet's catalog. And here I will deal with the structure of the code and what I did to solve some issues. In particular, when I first started my PhD, the first question that I asked myself was, how many exoplanets are there? And then I looked online on the form main in online catalogs, and I found this. And as you will see here, these are screenshots taken in the very same day. And there are various numbers of exoplanets known to those catalogs. So what's the right answer, you might say? And furthermore, I tried, first of all, to plot the data that this catalog had and find if, expecting some sort of overlap of all data, because data are supposed to be the same. That's not exactly the case, since if I did this plot, which is particularly useful for exoplanetary community, for the exoplanetary community, there are a few areas that are not uniformly covered, as well as theoretical parameters, as you will see with this line here, which are the theoretical theoretical data taken from actual measurements, and in the end, all catalogs had different sorts of data. So what was I to do? So I decided to develop a software from scratch. And this takes into account all sorts of problems that appeared in this catalog, such as the selection criteria, which is different from one catalog to another. This is due to the fact that in real life, we do not know what's a planet and what's not, because it's kind of debated in the community. It depends on the formation of the planets, or of the planetesimals, if they are actually planets rather than brown dwarfs. So, and also the four catalogs do different choices for what concerns both the update of the data frame as well as the choice of the candidates that are to be included in the tables. There are also errors that could be caused by different aliases, because stars are known with different names, and also with a different notation, slightly different notation. And for a human mind, as we see here, the very same star is reported in 4 different names in the 4 catalogs. For a human mind, that it's obvious that's the same star, but for a software that matches the strings, this is not obvious at all. And also, for what concerns the coordinates, Proxima CMB, for example, it has different coordinates in the various catalogs. This is probably due to the fact that we are only human after all, as we say. So there could be errors due to the update of the various catalogs as well. So ExoMeRCAT in this framework aims to provide a uniformity for all those catalogs and try to create a new data frame that it also follows VO standards and allows us to, any astronomer, to look for information for what concerns the star at any time in our analysis. And therefore, we wanted to provide a link that correctly links the planet to its source star data. And also, in doing this, we corrected all those errors, such as mismatches and coordinate errors, and we provide warnings to the maintainers of the catalogs that could therefore correct the errors. And we also have a graphical interface, as I will show to you briefly, because for people who do not understand either TopCat, since this catalog is in TopCat as well, or Python, they could use as well the graphical user interface. So, first of all, one needs to download data, and this is not the very same procedure for all the 4 catalogs. This is different. One could use command line or git comments, as well as tap queries to the VO service. And here is the first encounter with the VO, which will be very important in all the software script. First, and then we have to homogenize the various catalogs, such as they have the same number of columns and with the same headers, which was not obvious in the first place, because at first, when trying to merge them, the code did not recognize that, because the names were different. And in doing this, we also try to uniform also the names of the planets when possible, removing white spaces and all sorts of errors in the names. Then we perform some checks. First of all, we queried the mass catalog for Kepler and K2 objects of interest to understand what's the real status of each target, that at least for the transiting ones. And this table here provides us with the correct status for each planet, as well as its official name, which was not, which could not appear as the official name from the original catalogs. Then we perform some alias checks, since one could expect up to 4 occurrences of the same planet in the 4 catalogs. But they could have been known in via different names. In doing this, one should understand that that planet is actually the same. In doing this, we also queried with Simbad, the tap query with Simbad, in order to retrieve all the available aliases for the whole star, and thus this helped us a lot in merging at a later step. We corrected also the coordinates. We grouped the catalog and corrected when possible by choosing the most probable value, which is the mode of the subgroup of each host star. That was possible to do in most cases. When it was not possible, we didn't do it because we didn't trust the coordinates in the first place. But we can put a flag on that. At this point, here is the slide that Marco borrowed me. And at this point, we wanted to find a main identifier for the host star, that could allow us at any time to query the stellar catalogs for any sorts of statistics or study that we wanted to do, and not least, we wanted also to have a main identifier that could allow us a perfect match, that could allow us to overcome all those nomenclature problems that we encountered before. In doing this, we queried with the tap service of Simbad, Vizier, and all the most important catalogs that we have, and we ended up fulfilling this grid of main identifier. At this point, the 4 databases are ready to be merged, and with the merging, we selected only, for each data set, we select only the most precise one. That is the one with the lowest relative error. But that's a choice. That could be also changed by the user if needed. And in the end, we end up having a standardized catalog for the currently known exoplanets that could have also information concerning the original exoplanets, since one can also be able to trace back to the original data frame for every target in the catalog. And as I said, we provided also a graphical user interface that allows the user to download data and filter them, and also to produce some plots automatically. These are the major plots that are known and familiar in the exoplanetary community, but also the raw data are given to the user that in order to do all sorts of analysis. And these are the results. I repeated the software. I ran the software with and without the checks that I did concerning the status, the coordinates, and the aliases. And we find that with the simple match, that is the one not performing any check on status, coordinates, or aliases, we have a much larger amount of planets that are not recognized to be the very same. If we do the checks, the very same sample is much smaller, and we increase the number of planets that have 4 matches in the 4 catalogs, thus giving us much more realistic results, also in the number of exoplanets currently known, which is substantially different. We have 3,000 exoplanets that were not recognized as duplicates at first. And this catalog is weekly updated, and it is a VO resource. You can find it in as ExoMercat, in TopCat, and you can do whatever analysis you want. And that's basically it. I'll leave you with the conclusions. And take some questions if you want.
Okay.
Hi. In case of duplication of information, like different position, you choose the smaller relative, and the other position. But you said also that are available for the person.
Sorry, what?
That you say that it's possible to choose which point or which position to use it.
The code does choose the perfect one, the best one. And I mean, for what concerns the coordinates, if possible, it replaces the wrong coordinates with the mode, so the most probable ones, based on the other catalog. In fact, for Proxima here, this is the wrong one, and it would be replaced by either of these, because the others are all coherent and the same. For what concerns the data sets, for each parameter, that is mass, radius, inclination, and eccentricity, and all sorts of planetary parameters, we choose the most precise one. That means that for a given planet, we do not constrain the whole data set to belong to the very same reference paper. One should have within the same for the same targets many different papers and many parameters coming from different papers. And of all those parameters available, it chooses the most precise one. Okay.
Yeah.
Sorry, but this is one rule that maybe you might have heard around, is that never, ever change coordinates determined by other people. Yeah. You could, no, this is an important rule, because that's probably an object misidentification. So what I suggest is that I think you should talk to your colleagues at the SSDC, because we don't even pretend that Gaia is right when there is a mismatch in the coordinates. And Gaia usually has an error which is negligible compared to everything else. But we don't even trust that sometimes.
Well, in the end,
especially with the bright stars.
Sure. In the end, the final catalog has the official coordinates as retrieved from Simbad. So this correction for the coordinates is used only internally in order to help the code recognize the same planet. But in the end, what's the output is the official coordinates by Simbad. So at that point, I dare not say.
Consider Simbad coordinate as official.
I don't know. For sure, I do not want to put any change. If you want to look at the original coordinates, you can go to the original data frames. Yeah. Yeah, but the check is done only for the mismatches, and then I simply get what Simbad has at this point.
Okay. Thank you very much. The last of them this morning, Sandra. Okay, thank you very much.
Hi, so I'm going to talk about Breakfast. Breakfast is a suite of software tools that's made up of toast, cafe, cacao, and muesli. Now, all these packages are in varying stages of development. I'm going to focus on toast and cafe and cacao for the moment. So basically what I'm addressing in the software packages is the kind of questions we've discussed in the last couple of days. So the main questions that we're facing now is basically how do we connect previous results with data archives? What kind of data products do we actually need? And how do we present these data products in a way that one can actually deal with the big data? Because you need to have a way to filter the information. So just look at the data flow of how the connection between archives and the final published result actually looks like, which is very similar to what was presented already. So you have the data collection with your archives. They then go into databases, which can then be explored with tools. And what we then need is catalogs, but these catalogs need tools like classification tools, component detection tools, advanced imaging diagnostics, because if you want to explore all these data in a machine learning format, for instance, we need these kind of metadata and these cutouts I was mentioned before. And in the end, what we also need is a connection of those catalogs back to the archival databases for catalog generations and matchings of catalogs with archives. So first of all, I'm going to address the first question. How do we connect previous results with data archives? This is where Toast comes in. So at the moment, the way archives are handled, except for the ESO archive, which already goes very much in this direction, is that you've got your archives, which have the archive metadata, like what was observed, when and how. And then you've got your papers and your catalogs, which actually have the information of the scientific input. What we actually need is a connection between the two. So what would be great to have would be an archive where you can do a current search, and then within this current search, it gives you all the information, what was already published, what is the metadata available, what catalogs are available in that region, etc. So basically, what we need in the end is a combination of big data visualization, big data analysis, and big data database statistics, both from an archival as well as from a catalogs perspective. So Toast goes in this direction. What Toast aims to do is it aims to cross-match different catalogs and then to provide a way to visualize the metadata present in these catalogs, and then also to link it to archives that are already present, like the JVLA archive, the ALMA archive, even archives from telescopes that aren't existing anymore, like KAMA. So that's the interface we're offering. It's still in development, but what it actually will do in the end is to connect the metadata from your archives with catalogs from Vizier, etc., to give you an overall perspective of what was observed, when and how. For instance, if I want to have an idea of, I've got this area in the sky, I want to observe what line was observed there, when was it observed, what instruments were looking at this object, and what hasn't been done yet. So thinking in terms of proposal preparation, this is where TOAST comes in, because it gives you a way to filter your information and to produce samples from archives, data samples. Now moving on to the second and third question, like what kind of data products do we need and how to present the data products? Here is CAFE. Like CAFE is an existing web interface that produces advanced image diagnostics from archival images or in fact your own images that you put in. It works on the FITS image level and it works for a variety of instruments like ALMA, JBLA, Plateau de Beau images, etc. And the way CAFE was written is that it's all automated. It works within a web interface with a few single clicks. The idea is that you have the interface, you put into it your FITS files, which you either got from your archival database or the FITS files that you've generated yourselves, and then it does a selection. It automatically finds out whether, am I looking at a cube, am I looking at a continuum image, and then it generates keywords from those images. And it also does cube diagnostics and continuum polarization diagnostics. In the end, it also does subsampled visualization and classification. Now, a picture says more than 1,000 words, so this is the interface we've got at the moment. As you can see, all you need to do is import your FITS images and then click a few boxes of what you actually want, and it gives you the diagnostic plots. So this is what CAFE actually does. So you just insert a few FITS images, like cubes or continuum images, and it's all automated. It finds you a 3D view of your cube, it does 3D position velocity diagrams, it does line detection, continuum subtraction, and line fitting. It gives you a spectrum overplot over your image, and it also produces automatically moment maps position velocity diagrams along your major and minor axis. What it also does is that it does component detection in the image plane as well as in the cube planes. And you can also get polarization plots and light curves and also image cuts out of it. This is all automated. It all works on you go to the web page, you insert your FITS images, you click a few boxes, you let it run, and then the results come out, basically. What it also does is we're using AstroQuery to link the detected components that CAFE finds in the images with external databases like SIMBAT and NED. And you can actually plot the, if you've got a sample of images and have found the components in these images, you can plot the redshift distribution, for instance. And it also gives multi-vector projection plots if you've got a sample that you've inserted. Now, this is the interface. How we're actually using this at the moment is that we are basically running CAFE over the whole ALMA archive, only on public images. And at the moment, we have done 900 projects. To give you an idea, that makes about 40 to 45% of ALMA's cycle 0 to 4. And we just got a computing proposal accepted at Trieste CHIP to continue this work and to produce diagnostic plots for ALMA images. To then, in the end, produce samples. That's where TOAST comes in, from these large databases and to do science with it, which is what we actually want to do in the end. Those are only a few examples what CAFE can produce for an ALMA-based project. So you've got lens systems, galaxy systems, and galactic projects. And again, this is basically, you put in the image, you don't need to do any user interaction. This is the results that come out immediately. It's all automated. If you want to test or use CAFE, you can write to us, cafe@dira.inov.it, and we'll give you access to the web page. Now coming to Cacao. Cacao was written in the light of the first SKA data challenge. Now, CAFE works on small images and cubes, whereas Cacao works on larger fields. Cacao is a source detection algorithm, essentially. It was written from scratch, it's fully parallelized, and the SKA challenge results are not yet out, but we were happy with the result. And the next step in Cacao is to move it more towards the machine learning approach with Muesli. So this is the idea of Cacao. Cacao is basically, you put in the data It does some really simple data preparation. It then gives you noise diagnostics, source detection, source description, i.e. what flux am I seeing in the detected sources. And then it also does a very simple source classification. And with the machine learning algorithm that we're developing at the moment, we hope to be able to improve this. And this will go into the muesli package of the breakfast suite. Here are a few examples of cacao applied to real data. So this is an example for Gleam and Loafer and TGSS. Again, stressing the need also for cutout services, because if there weren't any cutout services, we wouldn't be able to run these tests on these data. So this is just, thanks. So I'm going to stop now with this overview. And so we really do need not only separate data archives and separate catalog archives, we really need the combination between the two. And we need tools that are easily accessible and metadata that is well described and is also linked with data archives. So, thanks.
We can talk personally in Bologna, but anyway, you didn't speak about programming languages, you didn't speak about how to feed the data in, and you didn't speak about the virtual observatory, if you can say something.
Okay. Programming languages, this is all written in Python, so cacao, café, muesli, and toast, all written in Python. Muesli involves TensorFlow and PyTorch. Virtual observatory, definitely very important. Thanks for bringing that up, because the catalogs which I'm actually using for toast are coming from Vizier, but also from papers which have tables which aren't yet in the Vizier catalog system. And your third question was how to insert the data. Yeah, so basically for Café, we just have a simple FITS file upload system with a limit at the moment on the data size, though, to make sure that just people don't just upload huge amounts of data and we've got control of what's uploaded.
Would it work for non-radio data like optical or infrared imaging?
I haven't tried it yet. That's you know, we can discuss that, but that would be great.
If there was a standard data access, could you point this at an archive and just reference, rather than having an uploaded file, just pull it? User could just provide a reference to that file and you would just pull it right out of an archive?
Well, what one can already do is one can use Astra Query, for instance. If there's an image archive cutout service, which has accessibility via a script, so then yes, that's really easy to implement.
Any other question before starting with?
Yes, first of all, I would like to congratulate with this very beautiful presentation and work you did. It's, I found it's a real example of high-level services that modern data center can provide, and so congratulations. I know how much effort need to develop something like this, and my question is exactly in that direction. How many people are involved directly in this?
Well, we have the whole AMA archive node, which is an assembly of 10 people. We were all involved in the Cacao Data Challenge. To give you an idea of the timescale, like Café was written in 2 months, Cacao was also written in 2 months, Toast was written in 3 weeks. So that's kind of the scale. I was a lot involved, and there's also Marcella Massardi, Andrea Gianetti, Jan Brand, we're all a team.
Not just you?
No.
Okay, thank you very much. So, Lino, so you can help me to the discussion, because before the free lunch, And I will use free lunch from Fabio Pasian. Thank you very much from everywhere. I can think we can start a discussion. One was about the DOI, was in program. I don't know if was planned. Yeah. Was planned from Sovereign about the example about the DOI in Canada, or to submit it, or you discuss mainly about the point we define. So about the future solution, about the DOI, the DOI activities and so on. Future solution, just we already talked that one point is also Filippo told before, but unfortunately probably he is working with the IVA from ISO or something like that. Another point. One point is infrastructure, one point is the peoples, one point is actually to understand what we have and what we need. I don't want to talk now about infrastructure. We are already talking about, explained that already have, already working. There is need a lot of real hardware, but this is another point that I think not to discuss here. But what about the future? What about the solution? What about what you need to improve the quality of the data and to have the possibility to use at the best our data to improve the science, to improve our career, and so on? Because I think the target is that.
Yeah, sure. As we started from multi-messenger. Mm-hmm. That requires fast access, because we saw two things. We need to be very fast, because in few minutes we need to know if that portion of the sky was already covered, because maybe we need the images, because we want to do images differences. And we want to know if then sources in this area are there. We want to know as much as possible about sources. Ideally, this should be done automatically in a programmatic way. So really, what is important to have this interconnection among all archives. Really, because we must be fast.
But fast, what do you mean? Because fast can means high-speed network. I think more or less we have it. But fast means easy access to the archive. Fast means easy define in which archive I go to make a search. Can be VO, for example, an example. But
fast means all.
Fast, yes, fast means all, of course. Yes. And we have to define which is the bottleneck for that. Where we can go to improve the fast access. Christina is something.
Thank you. I would like also to add one thing that is very important, probably most important for the past observations in data, that is the data curation. Some of our speakers notice that some metadata are not correctly filled into the files. So the description is not correct, how we can say, contains some errors, etc. One thing that we discovered for some telescopes was that data curation is not at all applied. So we have to deal with that. It is a nightmare. It is a nightmare because after 10 years, you cannot reconstruct what was the purpose of the observation. So now the new telescopes are, of course, well constructed in order to be not human filled in the data production. because every process is automatized. But for the past, and for this purpose, probably we enter also the multi-messenger. If we have to investigate past data, we have to provide, from INAF side at least, data curation for our telescopes and projects and etc.
Yeah, in fact, at least for the feed header, I think it would be already an achievement if enough contributed facilities, telescopes that use a uniform format. You can see VST, you can see Galileo, you can see REM, you can see whatever. Known have common keywords, at least the basic keyword, known, all different. And that's really something has not to be acceptable within, but we have it. So we start from these basic, simple things. Well, they were already at a good point.
Yes, but good data curation, I think that is coming from the data center, by coming also from the people that is working on that. If you want to take your data in your desk, this is not data curation, it's a curation for myself, very nice, very nice GIF when we tried, but of course, publish this data, publishing very well science, to be faster is the best way.
I don't know the Canadian experience on curation, where you grab metadata from other, you just take or you try to.
WCS. The FITS WCS paper, the WCS embedding in HDF files, standardize on that description as a first step. And I mean, the paper describes all the necessary keywords and everything. And that's a really good first step. And then at least you now have the physical characteristics. And also then the mapping from basically physical characteristics to pixels for cutouts. So it's all there. And that would be a first step. And that's what we've asked our data providers to provide as a minimum. And then other characteristics is really what you need for discovery. You don't need to describe everything about the instrument or anything like that, but really get to the discovery. So what do you need for discovery is those physical, the physical description, and maybe PI and observation ID and proposal ID and things like that. But it's really a minimum set, and it's getting everyone to agree to provide that minimum set, and not all their favorite metadata and describe their instrument. And we've had many battles with providers on this because everyone has their favorite and necessary keywords to be represented in the metadata that is queryable. It's a minimum queryable set that you need to agree on, and WCS is the first step.
This also answers your question if you can use cacao for optical. Well, in the radio world, things are much more uniform and similar in the various telescopes. In the radio, in the optical, it will be a mess. You should match a list of keywords to whatever. Not to speak about the word coordinate system that are not using the same keywords. You find different keywords, old P or whatever. So it will be a mess, apart from the density of sources in the sky. So definitely not. But still, in this uniformation, this homogenization process that we would like to aim, I think, again, a set of keywords. The hierarchy has been an attempt from ISO, but I don't know how many people are using ISO keywords, I'm not sure. But if you want to go toward the hierarchy is a standard. Let's go to hierarchy keywords, that's it.
Fortunately, hierarchy is not standard. It's an ISO extension of the FITS standard. It's an ISO standard, which is different.
Okay, also, OGIP is not standard, but they use it in high energy OGIP. So, if you don't like, the community doesn't like to have a common standard keywords, okay, let's go toward a coded set of other type of keywords that still are FITS keyword in any case. So, that's my point.
what you're saying is not exactly true, in the sense that for the VLBI part of the radio world, we are already using the FITS format since the very beginning, so it's the 60s of last century. And for what concerns the Italian single dish mode, we are using FITS standards since 10 years at least. Yeah, exactly. When I speak about the FITS standard, I'm speaking about the header keywords, not the binary stream of data, of course. Just to complete the landscape, just to add an information.
Probably you misunderstood completely what I said. I was saying that you can use in the optical infrared world a tool like Cocker, because the difference in the various keywords is much more wider than in the radio world, independently that you are using keywords in a FITS header or whatever. Okay, so the radio world is much more uniform. More standardized.
Okay, I understood that you were referring to the Italian facilities. So.
So I think
what kind of actions we could.
Deadline.
So the action is the main point is I need to access the data as fast as possible, but also this means to access to the computing infrastructure as much fast as possible, because I think you don't need only data, but probably you also need to analyze something like that. Like access to computing, like access to the data, I think we have many activities already started. Many is again to harmonize, again probably to understand which is the best way where to go to check something we have to do. About access to infrastructure with network, we already have a gigabit network like ICT, but we are going to increase. About access to computing infrastructure, we are working on that. There is some computing infrastructure is possible to access. At the moment, not very fast, because you want to access to Cineca, you want to access to chip, for example, you have to submit. But you're not interesting? No. No, let me know. Is that?
It's a strange body language.
Or you want to have your personal or infrastructure because you need to make SSH. I don't know which is the best way. Depends on the amount that the infrastructure that you need. Computing, hardware, and so on. If you want to have a best access and fast access. Best don't means fast, of course, usually. What are our needs, what is moving on, what we talk about the features. More data, more infrastructure, more computing science, more information, more discover information about any things. There is a lot of things that you have to do. But the users must tell me it. The user must tell me, I need this, I need this, I need this infrastructure, I want to help you to develop best these kind of infrastructures. So testing and so give you suggestion, give interaction, give you a little patient to do, okay, it's not working the first time, but the second or third, yes, because I know. But the users must be remembered that I need this. Without I need this from the user, I can talk with you, I can talk with Mauro, Nicastro, Luciana, and so on, but just 3-4 people is not the community, Roberto.
Again, sorry for English. Just a consideration. Probably we go again in the focal point of the discussion. We have identified a mediator, a person that collects information. What talk the colleague is, I want an answer very fast. Of course, if you have your environment, probably you optimize the process for a very fast, but now we have a new requirement. It's a multi-messenger fast action. The multi-messenger action is the synthesis of knowledge of measurements, knowledge of results, knowledge of process. So the focal point return in a group of people that give the dictionary, tell me this concept, the dictionary for translate the different requirement, because the astronomer is interested to go to the article. It is right, but he makes some wisdom for the enough. So I want to preserve, so data curation. I think there is a change of perspective in approach of the problem. And coming from two, come si dice, contrapposti, two different way to arriving to the goal. One way is from the past. We have made some errors in the past. We have to learn from these errors. Now we have a big challenge from big data, artificial intelligence, different methods. We have to monitoring this for give new paradigm in the solution. Just a consideration. And enough, of course, is the place where you realize this, of course. Sorry if I repeat, but it's the environment.
In the last 5 years, I always told, but I remember, I think that I told also in these days, if we are present here like outside, like enough, we are 1,400 people. So we are present like Trieste Observatory, because my observatory is just 80 nice people, but it is just 80 nice people, not more.
Yes, sorry, again, I'm me. I would like to move the discussion over another similar direction. That is, now we are talking about how to improve the data fundability, but we have to take in mind also that after that we have the data, we have access to the data, now the big project needs also support for understanding what the data is containing. Because, of course, when we will have SKA, for example, without an astronomer that support us in exploring the data that was taken, probably we cannot reach all the goals that we propose in the proposals. So the first point is to present the data as much as possible, complete, findable, fair, open, etc. But another thing is that we probably need also the user approach that needs someone else that help us in discovering and optimizing the data reduction that we want to do, or in the data center because the data is too big to perform it locally, or by ourselves if the data allow us to do it. So this probably also involved the next session, but I think that another role is not only for the data curation, but also for the astronomer specialist that helps in big facilities. Yes.
Any comments? Okay.
Just a quick one regarding what Christina just said. This, to me, again, goes in the direction of defining what we think as an infrastructure, because this is part of the infrastructure. The infrastructure is not only the APG high performance computing or storage or whatever you want on the more technological side. It's also this part, to me at least. We should start to define as a community what is our idea of an infrastructure. That's my view.
The community, that means, I told you before, astronomers, science computing, and so on. All the people that is involved. I think that one step was made from the president 1.5 years ago when tried to well define the difference between researcher and techniques, where researcher is one part of infrastructure, techniques, technological people, not techniques. Techs also be, but technological people is the other part of infrastructure. And of course, you want to make career, you want to create a data steward, another word that usually, your data steward should not be a science, only a science. Probably is more technological one, and this not means that you wrote article about exoplanet, but we wrote an article, probably in less number of that, about how to improve that infrastructure to discover exoplanets. And this means a career for the people. This means that you can be a technological one with you following how to development the infrastructure until that how to develop the exoplanet too. Sometimes it's not easy to take the difference, but I think it is important for the data steward in particular that is part of our future in this environment.
So just add another comment. At least for the space project, okay, yes, yeah, okay, infrastructures, people which know also the science, science part and the infrastructure part can link together the two tasks. Are already in place, okay, at the beginning of the mission, okay, because you cannot start with a space mission without to decide, okay, the infrastructure you need, the software system have to be developed, and so on. So, in enough. Maybe it's very, very important to make it an overview of all what we have in enough, because in enough you have already some figures like you speak about now, okay? But you need to collect together, okay, to coordinate, okay, and also you need maybe to improve this kind of human resource. But I think we need to start to know what we have, because I have the impression, the feeling, okay, that we don't know well, yes, the the state of art of enough, okay.
In enough is very different. Sometimes we are moving on. But sometimes very difficult to understand what we have, because if you ask the people, sorry, what do you have, or ask to the director, what do you have, and for example, what you already buy for your infrastructure, why do you want to know it? Just to know, because I have to buy a new car or not. Why ask me? You probably want to take me outside. This, this is one of the problems. Moving on, there is evolution about that. Also, Mauro, if H1 try to ingest in H1 also the expertise of the people about that. But usually is, or not somewhere, but sometimes the first question is, why do you want it?
Yeah, commenting on what Alessandra and Deborah and also you were saying, we clearly need a little bit of change in the cultural background in INAF, because for example, in Euclid, we started working a little bit side by side with people from INGV, and they are really a team. I mean, whatever one person does is to the benefit of the whole team, and everybody is part of the team, even if it's the last person who joined. In INAF, sometimes I hear people who think well, yeah, I mean, it's just 3 lines of code, you do your work, but I am the real scientist. I am the real scientist, ragazzino spostati, lasciami lavorare. It's still too often happening.
No, I think there is enough that there is a change of cultural change is moving in that direction. Sometimes it's difficult to path that direction, but I think we must come back of the computing and the archiving. We are to understand well the request, understand well what we can do, and what we have and what we're missing, because many times what we're missing we already have, but we don't know.
Now we had missed the point of reusability of data. Okay, so the data has to be reusable, and this could be done only for some telescopes or experiment, call as you like, but you can do it only if you got the support of an expert. Because if I'm an optical researcher, I cannot interpret correctly the radio data. Okay, so if I want to reuse the radio data, I have to ask somebody to help me in doing this. So this should be also the goal of INAF, to grow all the community, not just for sector. Okay.
Yes, this is a very good point. In my opinion, the focus of the discussion about this should be dedicated to the way that the investment of an infrastructure is done. In particular, if an institution invests on an instrument, I came from the LBT environment, so I remember that one night of observation of LBT is about $100,000 sorry. So if I make an observation on a target, I want as a PI, but also as an institution, I want to have an advantage on the scientific community in order to have the more possibility to publish the scientific result in a particular time, while these data are private. So the harmonization and the usability of data should be done, but only for the public data after the private period. This is very difficult to impose to instrument, infrastructure, and observatory a standard from the beginning of the data taking and data, while maybe in the virtual observatory concerns, this can be done. This can be done because you impose a standard for the publication of data. This is my opinion.
So I think we should listen to our Raya Stormer's colleagues, because they've been historical in Italy. They have a vision before the others, probably because they've been swamped with data since before we actually got all these optical instruments. My point is, have we given up completely the idea of, remember, a few years ago, there was a call by INAF, different president, called for a national facility. Is that idea completely gone? Why we don't start from there? I mean, so let's be specific here, okay? Since we're talking about where many centers, we would be distributed. We had this idea. I'm sure Fabio remembers this. We had two proposals at the time. We could even make just one, okay? But this two was okay, okay? But then, no, remember? And then we discovered that the operation was for something else. But the point is, so as I said, we're missing the infrastructure. So that's why don't we do this? I mean, it's.
Yes, I would like to say something about the fact that people needs to have a multi-wavelength approach without having the deep knowledge that is typically requested for the guest observer of a single, a specific instrument. This is something that in INAF we already have, because in the Space Science Data Center there is a multi-wavelength approach, easy, because there was invested a lot of time, a lot of efforts, and a lot of money also to develop those high-level software products that are needed just to allow people not expert in specific, astronomers, professionists, which are not expert on a specific aspect, on a specific wavelength, to access and use in the scientific sense, in the sense that they can publish then their results, also in the other wavelength. I touched with my hand because meeting the very high energy astrophysicists, physicists and astrophysicists involved in CTA, but mainly MAGIC and DES, they are using a lot the facilities of the Space Science Data Center, because they could easily access gamma ray, X-ray data that are very important for the very high energy, to match together the very high energy data. But also, for example, they can access Herschel data, so infrared data that are useful as well. So I think that it's very important to, under the scientific point of view and under the astronomical point of view, to go toward the development of such high-level tools. That I think that this is the most the added value that an astronomical community can provide to this kind of activity, because you can buy the computer, you can pay people to manage them, but from the astronomical community you can have that added value that produce science and produce knowledge.
Yes, I have a couple of comments. One is related to what Angelo was saying, in the sense that receiving feedback from the users is essential. And we really benefited from having, let's say, a user committee, which was a formal body
that was requested and foreseen in our management structure. So this is something that could also be taught, for instance, in general for the ICT activities within INAF, so having some formal user committee which is appointed in order to make suggestions and raise use cases, so forth and so on. And the other comment is related to the fact that space missions, since as Deborah was mentioning, for space mission you need to prepare the ground segment well in advance before the mission is launched. So you need to take care, design, prepare the software, the archive, and all the infrastructure and all the pieces that you need in order to go from raw telemetry data to actual science. So to some extent this was important for us because it helped in having something organized and structured, and so in exposing our data in a consistent way to the community. So the things of having instead for the ground-based observatory, having small projects, small individual projects, but there are a number of data that are still hidden in the lockers, right? So this is a real problem that also require a change in the mentality, in the sense of being aware that the data that we receive, because we are granted time on a given telescope, it is not our own, but since this is paid on public money, we have at some point to make sure that the data will be available to the public and to other scientists and researchers.
Fabio, mi permetti di rubare una parola in italiano, sorry for English people, voglio dire una cosa un po' più particolare. Qualche volta mi sembra strano che se tu lavori per uno strumento, in questo caso tipo Euclid o tipo Planck o tipo altri, allora tu accetti di stare all'interno praticamente delle regole che sono molto stringenti dal punto di vista dell'organizzazione. Mentre se lavori per l'istituto che ti paga, queste regole non devono valere.
C'è un'incongruenza. Okay, I've got 2 points. One about the astronomical expertise that we need to handle data, and one on the proprietary part that was mentioned, I think, by Stefano before. Of course, I completely agree with Angelo, what he was saying. He was saying that tools are needed to allow people not having specific expertise on the instrument or even on the domain to be able to handle the data. That the data should be science ready or even web ready, which is a new word. But to do that, and here is an answer for Christina, you need at the data center people collaborating, knowing very well the data, so that you are able to provide the data in the way that Angelo was mentioning, that SSDC is doing. So both of you are right, basically. And the point is also, okay, let me say one thing before. About the proprietary data. One has to think the way that you handle the data and you store the data, you ingest the data in the archives. That sort of mechanism of flow has to be planned in advance, so that when the data become public, then they can be immediately opened. It's not that first you hide, you do your own stuff, and then you let the data become public. The point is that the data have been already pre-digested, possibly using worldwide accepted standards, maybe, not to reinvent the wheel every time. Then you have the ownership on the data. Policies may be also of the kind that you don't even see the metadata. You exploit them as long as you can, and then the data become public. Because you have to think things in advance. I mean, let's not think that we are smarter than the average of the people around the world. LSST is being defined as a software telescope. And the way they are doing it is VO first, guys, because these data are going to become public. So we will first think how we ingest the data so that they are VO accessible. And then they care about all the rest, because that's the plan. And I think that what we miss and have missed for many, many years here is actually a plan.
Oh, okay. To echo what Fabio said, because, I mean, the CDC operates this way. It comes in, every observation has a release date. So it's not even a mechanism. As soon as the data, that release date is hit, the data is public. So there's the first step. And the second step is that the VO standards now support authenticated access, and even the metadata in the TAP services can be protected, in the data services they could be protected. So while that release date is in the future, only the PI group can access the data. So there's interoperability can support authenticated access for proprietary data.
Two comments. First thing is that I would like to put my signature below what Fabio and just said about the proprietary period and this type of description of the data. The proprietary period is not intrinsic in the data. It's something that you attach on the data. The way you describe the data and the way you prepare them for scientific use come first, and that must be the same independently on the fact that data will be proprietary for some time or not. This is fundamental for me for the future. So I totally agree with you. And I would like to push forward what Angelo said, because what he said is perfectly true. I agree completely that what an archive or what an infrastructure might offer is are all the tools as far as possible that are needed for even non-expert users of the archive to exploit the data. That means that what Christina was saying, speaking about the astronomer offering support, comes before. You don't see the astronomer maybe when you go to the archive, but at some point something has been done by a mix of astronomers and technologists to prepare the tools and the things that are needed to interpret the data. What I would like to stress is that enough is composed by space missions, ground-based missions, many different wavelengths. Let's try to put everything together. I mean, starting from what is existent, which is important, interesting, and offers already many, many things. Just to recall what Mario Lattanzi was saying, he said we should maybe learn something from radio astronomers. Well, we should learn something from everybody of us. Every section of us has something to put on the table, to contribute. Space through the SSDC and all the other missions managed by maybe ESA directly. I don't know, I'm not an expert. Ground-based telescopes in the different bands, optical, radio, everything. I think that we are a national institute. We cover many, many different types of facilities in terms of wavelengths, in terms of how do you put your instruments, and also the type of collaborations that you have. Because when you speak about national facilities, it's different than when you speak about international telescopes like LOFAR or SKA. all these things should be thought about by a community, and a vision should come out from us, maybe. And this vision should be proposed to the top of the institute and all the people that then are due to translate this into something operable. That's it.
Very much connected with what just has already mentioned. But the point is that actually maybe a little bit provocative or naive question. The contracts, so that it's dealing with data. Enough? Enough? No. No? No. The idea is that INAF, okay, knows all the contracts. It doesn't matter whether they're space missions or they're telescopes or whatever. So if you put something in these contracts that oblige that INAF takes this data in national facility, and this, okay, there should be a copy, okay, in ESA, should be copy, or okay, in the facilities in the countries that they have this data. But we should have a copy, like institution, of this data, because there are people that collaborate to this data. So if you have a national facility, INAF should control this, because in every contract, just put one paragraph. Take all the data should be available with all the regulations, because yes, NASA, for example, gives some period of time to release the data. ESA for different space missions, okay, it's 6 months, but can keep track on this. If we put it after some period, because of course you have a raw data, you need to take care, because otherwise, if the data once is published to the community and there is something that should be calibrated after, it's a bit dangerous. Not the question is that you lie with your data, but the question is that some people that can use the data not in an appropriate way, so we have to be careful of this. But if we have some rules within the community, because INAF has so many institutions together with different projects internationally, just put some paragraphs in the contracts with INAF, with the Space Agency also, with SDC or with ASI, with everyone, so we have one paragraph and everything will be okay, because they're obliged anyway.
Yes, just to say that I was not pointing out on space with respect to ground base, because let me say that originally the ASI Science Data Center was mainly centered on high energy astrophysics. Then after INAF entered deeply in the management of the ASI Science Data Center, started also to work on space mission at large at all wavelengths. And this approach, but my point was not centered, of course, on the space or on the ground or on different wavelengths. What I was saying that it's a different approach. If you, I tried to say also yesterday during the discussion, if you are thinking to a data center that is part of an astronomical observatory, of an instrument, it's mandatory for you to have the data organized, prepared, and collecting all the information to provide the maximum usability and reusability of the data. But if you are thinking to something that is an upper level, so you can provide an easy access to everyone, this is a different approach. So first of all, we have to understand very well which kind of approach is important for us. And I think that sometimes in the discussion, these two aspects are always not very well distinguished.
I didn't want to talk many things because I am a sort of outsider, but probably I am the one you want to give the data. So, no, I just wanted to tell that in our case, first of all, as you was suggesting, we have many, so the so-called tier 0 in different places where we store the data, and not only on disk, but also on tape. In particular, we have this CNAF, we have the tier 0 at NICAF, then we have these machines in the States, at least 2. Okay, so different places for us where we store all the data. Then there is this preliminary digestion where we produce the calibrated data, which are much less, no? We pass to this 3 terabytes per year per detector. And this is what, again, is copied in all our places, also in small farms, which we have, for example, in Rome or in other places, and which are a part of the data which we distribute to the community. And there is the problem which was posing with the community, because something, if the community is you, or is a student in a school who wants to analyze the data, it's very different. Not only the quality, the data which you have to share, but also the software. Because for you can distribute also all the data, and we trust that you know what to do. But when we want to reach students or taxpayers, we want also to guarantee that they can reproduce our results. So we also share all the software which was used for that particular analysis, so that they can take the data, follow instructions, and say, okay, this is exactly the peak which was produced. And then they can do other things. But this costs a lot in terms of human effort, no? Because to distribute the software is very easy, but then you have to simplify the cost. Then you have to clarify what to do, how much the filter is done, when data are not stationary. So all these kind of things which for us are natural are not so easy to be shared, but we are really convinced that we want to reach taxpayer in the sense that we want to reach students, at least. And so you have to, so the problem is at different levels. And so in our case, we distribute all the data, but also triggers, interesting data, FFTs, so data, so the problem is complex, and but I think that once one starts to enter in this business, then one has to follow all the channels, because we have to reach many different communities.
Yeah.